Hey everybody, this is our lesson on fission and fusion, and by the end of this lesson you should be able to compare both nuclear fission and fusion. So let's just first talk a little bit about nuclear forces that we come in contact with, and this is an attractive force that binds protons and neutrons together in the nucleus, and we know based on like radioactive decay that the nucleus is what changes. And because this strong force does not depend on charge, it acts on and protons and neutrons together. Over really, really short distances, this strong nuclear force is much greater than the electric forces among the protons in terms of, like repulsions or attractions to electrons, which is also one reason why they don't collide into the nucleus. Electric forces in the atomic nuclei depend on the number of protons. So the more protons you have, the more electric force you will have, which is also known as Coulombic attraction. And that is what actually tends to make those protons repel each other, which makes them a little bit easier to manipulate in nuclear decay. The larger the nuclei, the stronger the repulsive force is than in a smaller nuclei, because you've got so many more positive particles interacting with each other. The nucleus will become unstable as it gets larger and larger, and that tends to make it radioactive, which means when your strong nuclear force cannot overcome the repulsive electric forces among the protons. So the protons and the neutron nuclear force is weaker than the repulsive force, and that's what tends to make these nuclei break apart. So now let's talk a little bit about fission, since we're talking about breaking apart. And this is the splitting of an atomic nucleus into two smaller parts. So fission is breaking apart. In nuclear fission, a whole lot of energy is given off by very, very small masses of atoms. That's why this is super efficient in terms of producing energy. It's just not very clean. During this fission reaction, some mass seems to be lost from the reactants to the products, and that is what is converted into energy and used as energy. The relationship is shown in Einstein's mass energy equation. So if you've ever heard of E equals mc squared, that's where this is coming into play. And fission, and here's the symbols for that equation. According to the law of conservation of mass or energy, the total mass and energy must remain constant from one side to the other. So we do have to recognize where that goes and where it came from. But what we look at with fission is a neutron will bombard a radioactive isotope, which will then split apart and release more neutrons to cause more of these fission reactions to occur, as you can see in this little GIF here. And that's what we call a chain reaction. So a chain reaction is multiple fission reactions occurring in a series. So if a neutron is released during the splitting of an initial nucleus, and that neutron will then trigger another fission reaction to occur, which then will trigger another one, and so on and so forth. And the speed of the chain reaction can vary depending on if an atom needs to be hit by more than one nucleus to break apart. In order to sustain a chain reaction, each nucleus that is split must produce on average one neutron that causes a fission of another nucleus. So if more are produced, the faster this chain reaction will occur. And once you have elements that are not splitting off neutrons, your chain reaction is going to fall out. And we look at critical mass when we look at a chain reaction, which is the smallest possible mass of a fissionable material that can sustain a chain reaction. So we can use big particles, but the smaller it gets, the slower or less likely this chain reaction is to occur. So here's an example. You've got one neutron that's going to hit this first particle that's going to break off neutrons, which are then going to break other ones, and so on and so forth, releasing energy at each step during this reaction. which is why fission is actually what we see happen in nuclear power plants. So these will generate about 20% of the total electricity in the United States. And this, I will say, this percentage might be off. My information is a couple years old, so it could be a little off here as we are trying to move to more and more green energy sources. And in a plant, we use the controlled fission reaction of uranium-235, and it occurs in a reactor. And there are some concerns with power plants, just as there should be, such as radiation exposure, nuclear waste. How do we store it? How do we get rid of it? How do we keep it from being exposed to the surroundings? And then also, basically power plant meltdowns, right? We don't want that to happen. So if an operator loses control of a reactor or a cooling system that is running around these reactors fails, then you could have a meltdown and have the radiation spill out into surrounding areas. So you can think of like Chernobyl, 3 Mile Island, just as two examples. There are a bunch of examples where nuclear power plants have basically broken down and released a lot of radiation in surrounding areas. So now let's talk about fusion, which is the opposite of fission. And this is the coming together of two nuclei. So they will form a much larger stable nucleus. As in fission, fusion is a small fraction of the reactant's mass, and that's converted to energy. This is actually much cleaner than fusion because the products are more stable as opposed to releasing more radioactive isotopes. The only problem with fusion, which is why we can't do it, it is not cost efficient or feasible. The temperatures needed to make this occur and the energy needed to make this occur are not worth the amount that you get out. So it's not cost effective. For fission, you put a little bit in, you get a lot of energy out. Here, you got to put a ton in and maybe break even because the temperatures have to be so high and the matter has to be in plasma state. So where we tend to see fusion reactions occur is on the surface of the sun. And just for definition's sake, plasma is the state of matter in which atoms can be stripped of their, I don't know why that's typed in there twice, stripped of their electrons. So this is what a fusion reaction looks like, where two small atoms are brought together to form a new nucleus or a new, stable, larger atom. Great, guys. So now hopefully you can